All right, now we know exactly what complex numbers are. The set of complex numbers is just a set of pairs of real numbers equipped with addition and some special multiplication, right? But our original motive for complex numbers was to solve quadratic equations. So how are they related to each other? And we study that connection by showing how to find the square root of a complex number. The square root of complex number is defined as follows. Well, a square root of anything actually. So let's say we have a complex number, a plus ib. Of course, a, b are real, and I is the imaginary unit. Then the square root of this complex number is a complex number, let's say x and iy, such that if it is squared, then it gives the given complex number. So this is called the square root of this complex number. So let's find the solution to this equation. That means what are the values of x and y which are real that satisfies this equation for any given a and b. So to do that, we first expand this left-hand side, and that becomes x squared minus y squared plus 2xyi. So this is equal to this. So the real part is x squared minus y squared, which is equal to a, and the imaginary part is 2xy is equal to b. So we have these two simultaneous nonlinear equations for x and y. Okay, so now we want to eliminate one of the variables, x or y. So let's use this second equation. So let's eliminate y. So for that we do like this. However, x can be 0, and it's not guaranteed that it is not 0. So we cannot just do this. So what if x is actually 0? Then 0 times y is 0, so b must be equal to 0. So maybe it's a good idea to consider the special case where b is 0 first. And case 1, if b is 0, okay, then that means x, y is 0 from the second equation. So that means x is 0 or y is 0. Okay, so if b is 0, then it's just a real number. The given complex number is actually a real number. So we want to find its square root. So if a is non-negative, then its square root is just square root of a. So that is the answer. And of course, it's plus minus, so we have this. And if a is negative, then that's a problem. And in that case, if we look at this, since x and y are real numbers, x squared and y squared, each of them cannot be negative. So if a is negative, then and b is 0, so either this is 0 or x is 0 or y is 0, but y cannot be 0, x must be 0, because otherwise so if y is 0, then x squared is always positive, non-negative, so it cannot be negative. It's impossible. However, if x is 0 and y is not 0, then negative y squared can be negative. So that's it. And if that's the case, then y is equal to plus minus square root of negative a. Of course, negative a is positive, so this square root is already well defined. So in summary, if a is non-negative, then we have square root is x plus y is plus minus square root of a. So x is this and y is 0. Okay, and if a is negative, then that's plus minus square root of negative a. Okay. Now the second case, b is non-zero. Okay, let's write the equation again. And 2xy is equal to b. Now b is non-zero. Then this means neither x nor y is equal to 0. So x and y are non-zero. It's guaranteed because of this. Okay, now we can get rid of y by this substitution. So this into the first equation, we have this b2x squared is equal to a. And multiply both sides by 4x squared, and we have 4x squared and b squared and 4ax squared. So if we put t equals to x squared, then we have just rearrange this one, and we have 4t squared minus 4at minus b squared is equal to 0. Now, this is a quadratic equation for t. So we can, let's apply the formula for the quadratic equation. And that becomes, what is it? Let's see, that's 4, so 2a plus minus square root of 4a squared plus, because of this minus sign, that's 4b squared over 2. And note that inside this square root, it's non-negative. So there's no problem with this. We can use this as we know it. You know, this is defined only for real solutions, and it is real solution. So let's take out, oh, wait a minute, this is 4, it should be 4 here. And take out this 4 out, and they are a factor of 2, and they are cancelled. So that's a plus minus square root of a squared plus b squared over 2. Now, there are possibly two solutions here. So a plus minus square root of this. Okay, but actually this negative sign cannot happen because t is actually x squared, right? So, and x is a real number, so it must be non-negative. However, since b is non-zero, a squared plus b squared is always strictly greater than a, or plus minus a, or absolute value of a. So a minus this thing is negative. Therefore, this negative sign cannot happen. So what we have is x is equal to a plus a squared plus b squared over 2. And this can be positive or negative depending on the sign of a. It cannot be negative, right? Yeah, it cannot be negative. It cannot be negative because of this, so we can just take the square root of everything here. So x is equal to plus minus square root of a plus square root of a squared plus b squared over 2. Now let's put this thing into this equation. So y is equal to b over 2x. So x is plus minus a plus b squared and 2 squared. Okay, so let's cancel this 2 with this square root of 2 and plus minus b over square root of 2. And we have here a plus square root of a squared b squared. And let's simplify this thing by multiplying this. Negative a plus a squared plus b squared. Okay, to both numerator and denominator. Okay. So on the numerator we have this negative a square root of a squared plus b squared. And here, now we have this thing, square root of a squared plus b squared here. And we have negative a and positive a. So that becomes everything square root. So square of this is a squared plus b squared. And this, so square root of minus square root of a squared. So that is just b squared. And square root of b squared is maybe anyway. So this thing is the absolute value of b. So let's simplify this a bit. So b over absolute value of b and everything here. Two. So this 2 comes in here. So this is what we have. So this thing, so b over the absolute value of b, what is it? So if b is positive, then the absolute value of b is 1, right? So this is equal to 1 if b is positive. And this is equal to negative 1 if b is negative. And we're assuming b is non-zero, so we do not consider that case here. Okay, so let's call this, so let's name it as a function, sine of b. Okay, so this way we can write y as plus minus sine b of this. Okay, so this plus minus sign, by the way, x was this, plus minus square root of positive a. Okay, so when x is plus, y is plus. And when x is minus, y is minus. Okay, so there's correspondence. Okay, so if b was non-zero, then we have this. So the square root of a, so plus minus square root of a plus ib is plus minus square root of a plus square root of a b squared over 2 plus sine of b and minus a b squared over 2. So this is it. Okay, so this is when b is non-zero. Actually, this solution includes the case when b is equal to 0. If we define this sine function as this, so when b is non-negative, then sine function, this sine of b is positive 1. And when b is strictly negative, then this function is negative 1. So let's see that. So if b is equal to 0, then if we substitute b equal to 0 into this equation, then we have a plus square root of a squared is this, and over 2 plus, so because of the definition of this function, it's positive, okay? So wait a minute, we have I here, and that's negative a, and b is 0, so it's absolute value of a over 2. Okay, now if a is non-negative, then this becomes, so absolute value of a is just a, so it's 2a over 2, so that's just square root of a, right? Of course, we need plus minus here. So plus minus this, and so this is positive a, so minus a plus positive a is 0. So it's this. And if a is negative, then the absolute value of a is negative a. So a minus a is 0. And negative a minus a plus negative a is negative 2a. So that's negative a. So that's plus minus I square root of negative a. And this is exactly the result we have got before, or when we examine this case. So to summarize, the square root of a plus ib is this. I don't write it anymore. So whether b is 0 or not. Now let's see a few examples. First of all, what is the square root of negative 1? So that's plus minus. Okay, first let's just use that formula here. Although I do not recommend memorizing this formula, because this is quite complicated and eventually you will forget. So I recommend just following this procedure every time you encounter the problem of finding the square root of a complex number. But anyway, if we apply the formula, so this is negative 1. And of course, we know this is plus minus I, but let's apply the formula first. So that was a plus square root of a squared plus b squared over 2 plus I, and sine b, and square root of negative a squared plus b squared over 2. Now a is negative 1 and b is 0. So that is negative 1 and square root of negative 1 squared. Right? And sine b here, b is 0, so sine of b is 1, so it's positive. And negative a is 1, and square root of negative 1 squared here. So now this is negative 1 plus 1, that's 0, and I, and this is 1. So indeed, this is I. So of course we need to add plus minus here. So plus minus I, as we expected. Next, let's find the same answer by the first principles. That means, so if the square root of negative 1 is x plus iy, then if we square this number, we should get negative 1, right? So let's expand this, and we have x squared minus y squared plus 2i xy is equal to negative 1. So the real part is x squared minus y squared is equal to negative 1. And the imaginary part is 2xy is equal to 0. Okay? So from this, either x is equal to 0 or y is equal to 0. But y cannot be equal to 0 Because if y is equal to 0, then we would have x squared is equal to negative 1. But x is a real number, so if squared, it cannot be negative. So this is impossible. Therefore, x is equal to 0. Okay? So we have y squared is equal to negative y squared is equal to negative 1. So y squared is 1 and y is plus minus 1. So therefore, the square root is 0 plus I plus minus I times 1. Okay, that is plus minus I. So that's the same answer as we expected. And next, let's find the square root of I. Okay, I is of course the imaginary unit. So from the first principles, okay, so x plus iy squared is equal to I. So expand this. Is equal to I. So the real part is 0. And the imaginary part is 2xy is equal to 1. Okay. So let's see. From this we have, let's see how it's. So from this one we have x is equal to plus minus y. Okay. So if x is equal to y, positive y, then we have from this one to x squared is equal to 1 and x is equal to plus minus 1 over square root of 2. And of course this is equal to y. So in that case we have plus minus 1 over square root of 2 plus I 1 over square root of 2 as the square root of the imaginary unit. Okay, so what if x is equal to negative y? Then what happens? So in that case, from this second equation, we have negative 2x squared is equal to 1. But this is impossible. Because x is real, so x squared cannot be negative. So it's impossible. So this choice is eliminated. So the only possibility is this one. And we are done. Okay, so now that we know how to find the square root of any complex numbers, we can solve the quadratic equation for any coefficient. So A, B, C are real and A is non-zero. For any combinations of A, B, C, as long as A is non-zero, we know how to solve it. And the solution is always within the set of complex numbers. Now, let's review what we have done along the way. In order to solve a linear equation where the coefficients are real, the solution was always within the real numbers, right? It was okay, and we can always find the solution as long as solutions exist. And in order to solve the quadratic equation for real coefficients, and A is non-zero, the solution exists within the set of complex numbers. Okay. In other words, we needed to expand the set of solutions from real to complex. Okay. Now, what about cubic equation? So x cubed is involved. Cx and t equal to 0, and the coefficients a, b, c, d are real, and a is non-zero. Then does the solution always exist in complex numbers? Or do we need to expand the universe of numbers so that we have to define some new kind of numbers that includes complex numbers as a proper subset? The answer is no. Actually, there do exist all solutions within the set of complex numbers. And more generally, if we consider the polynomial of order n, so coefficients an, x to the power of n, an minus 1, x to the power of n minus 1. So n can be any natural numbers, and a1 x plus a0 equal to 0. So each ai is a real for I from 0, 1 up to n, and an is non-zero. So for this equation, can we find all the solutions within the set of complex numbers? And the answer is actually yes. And this is a famous theorem called the fundamental theorem of algebra. Fundamental theorem of algebra. So for this kind of equation of polynomials of order n, there exist n solutions. In the set of complex numbers. And n solutions means we can count, sometimes the solutions may be redundant, so there may be same numbers within in this n solutions, but counting this redundancy, there are always n solutions within the set of complex numbers. And actually we can extend this theorem so that the coefficients are complex. Okay, so for complex coefficients, we still find solutions in n solutions in complex numbers. So that's called the fundamental theorem of algebra. And the proof of that is beyond the scope of this lecture, so I don't do that. But it's good to know this fact exists. Okay, so that's all for this video, and see you later.